We'll start this video by announcing as a couple of theorems two amazing results due to Augustin Louis Cauchy. These are known as the Cauchy residue theorems. And the first theorem is that if f is analytic in the interior of a simple curve C, then the closed integral of the function f around that curve is equal to 0. And also, the second consequence is that if a is any point inside that interior, the value of the function at that interior point is given by the following integral. It's 1 over 2 pi I, the closed integral around C of f of z divided by z minus a. By the way, there's a corollary to this, an easy corollary, which can be gotten by differentiating under the integral sign and induction, and that is the nth derivative with respect to a at the point a of f is given by n factorial over 2 pi I, the closed integral of f of z dz over z minus a to the power n plus 1, which you can immediately get by differentiating under the integral sign n times. So the beautiful thing about these two theorems of Cauchy are that you can find the value of a function in the interior of the domain by simply looking at its value on the boundary C, because C, remember, is the boundary of this domain. And the interior points are the murky places where you don't know anything about it. Let's imagine there's quicksand. You don't want to get into the quicksand and take a measurement at point A, but Cauchy's theorem says no need to do that. Just go around, take measurements around that, and integrate those measurements, and the answer is going to be Fn at A. So this is one of the most remarkable theorems in mathematics. Now, last time, I also talked about Laurent's theorem. And the Laurent's theorem can actually be proved by Cauchy's theorem. So that's an easy exercise for you if you're interested. But right now, I'm more interested in computing residues, since it turns out that if you compute residues, you're essentially computing these big integrals. So let's first of all just define what a residue is. If you have this function f that can be written in a Laurent series, sum from n equal to 0 to infinity, an z minus z to the power z naught to the power n plus sum of n equals 1 to infinity, bn over z minus z naught to the power n, you can show that using this Cauchy's formula, 1 over bn is 1 over 2 pi I, the integral around the closed curve C, f of z over z minus z naught to the power negative n plus 1. Okay, so the quantity b1 is extremely important, and b1 is called the residue of the function f at z equals z naught. It's known as the residue of f at z naught. Now, if you look at the b1 here, b1 is going to be 1 over 2 pi I, the integral of f of z, z minus z naught to the power negative 1 plus 1, which is 0. So we immediately get this important formula known as the residue theorem. And that is the integral of the function f of z dz is just 2 pi I, because I can take the 2 pi I to the other side, times B1. Now all these B1s are included, so you'll write the sum of all the residues in the interior of the domain C. So this is known as the residue theorem. Let us actually compute some residues. So let's try finding the residue of the function f of z equals 1 over z squared minus 5z plus 6. First of all, you need to identify where the trouble points are. So one good way to do this is to FOIL it. So I get z minus 2 times z minus 3. So this has got simple poles, which means that the order of this term is 1 and 1. Those are called simple poles at z0 equal to 2 and 3. The residue can be found by simply multiplying by the corresponding pole structure and taking the limit. So this is going to be the limit as z goes to 2 of z minus 2 f of z. Because if you look at this Laurent expansion, if you multiply both sides by z minus 2 and take z to 0, all these a naughts will be gone, and then all these will be gone except for b1. So that's the purpose of multiplying by z minus 2. Now when you do this, there's only b1. There's no higher terms, by the way. So this gives me limit as z goes to 2, 1 over z minus 3, which is minus 1. Similarly, we can do the residue at 3. It will be the limit as z goes to 3 of z minus 3 f of z, and that's going to be limit z goes to 3, 1 over z minus 2, which is going to be plus 1. So we have computed the residues in this simple example. Now if you, let's take another example. What if you had a function that's slightly more complicated? Suppose I have g of z equals e to the 2 pi I z divided by 1 minus z cubed. So here you notice that there are simple poles whenever you have z cubed equal to 1. So z cubed equal to 1 means the only solution is not 1, because you can have the cube roots of unity here. So the solution to this is z equals e to the 2 pi I n over 3 with n equals 0, 1, 2. If you are interested in plotting this solution set in the complex plane, that's the imaginary part and that's the real part. For n equal to 0, you just get 1, which is the most obvious solution. For n equals 1, you get 2 pi over 3, which is 120 degrees. So that's going to be over here. And for n equals 2, you're going to get this third solution. And so these are the 3 roots of unity, and they lie in a circle of radius 1. So it's like your basic peace sign. So we have to look at the residues at all 3 values. So when you have a ratio of 2 functions, then you can use the property or the principle that the residue, so here's a lemma I'm going to quote. Lemma means small result that's easily proved, and I urge you to try to prove it. If you have a function f that's equal to g over h, and let's say if h of z naught equal to 0 is a simple pole, observe that these are all 3 simple poles, because if I write z as a factor, 1 minus z cubed as a factor, there will be 3 non-repeating factors. Then, and if g of z naught is analytic, the residue at z naught is simply given by g of z naught divided by h prime z naught. And it's an easy enough thing to prove. So I'll use that. All right, let's try this. G in this case is e to the 2 pi I z. So the first residue we have to compute is the residue at 1. Well, that's just going to be this function. Let's call this function f1 and let's call this function f2. So it's going to be f1 at 1 divided by f2 prime at 1. f1 at 1 is just e to the 2 pi I because z equals 1, and f prime is negative 3z squared at z equals 1. So that just gives me e to the 2 pi I is 1, and so that's negative 1/3. Let's try the residue at the next root of unity, which is e to the 2 pi I over 3. So I get residue at e to the 2 pi I over 3 using the same theorem. It's going to be f1 at e to the 2 pi I over 3 divided by the derivative of the denominator at the same value. So now it's just a matter of doing this computation. When I substitute e to the 2 pi I over 3 in the numerator, I'm going to get e to the 2 pi I. I'm going to expand what e to the 2 pi I over 3 actually is. It is cosine 2 pi over 3 plus I sine 2 pi over 3. And now the derivative is again negative 3z squared, but at this new value. So that's negative 3 times, when I square this, I get e to the 4 pi I over 3. Let's proceed to simplify this. Cosine 2 pi over 3 is cosine 120, which is negative half. Sine 2 pi over 3 is the same as sine of pi over 3, so that's going to be root 3 over 2. This is giving me e to the 2 pi I negative half plus I times root 3 over 2 divided by 3 times e to the 4 pi I over 3, that's over here. So we're going to get both of them are going to be negative, are they not? Because you have sine and cosine both negative, but that negative sign will cancel with this, so I won't write the negative sign. I'll get 1/2 plus I root 3 over 2 because it's just a reflection of that one. Okay, so this is the answer. If you simplify this, I can write this as e to the minus pi I times I is minus 1, so that's just e to the minus pi root 3, since the 2 here and the 2 there cancel out, divided by 3 times 1/2, so I'll pull out a half, 3/2, 1 plus I root 3. So that's the answer. Doesn't look super elegant, but that's what it is. And if you do the same thing with 4 pi I over 3, that's the one that's remaining. I'll not bother showing you the details, but I'll just tell you what changes in this computation. First of all, the numerator will stay almost the same. Okay, so I'll actually, you know what? E to the minus pi I is minus 1, so I can simplify this even more. That's minus e to the minus pi root 3 over 3/2, 1 plus I root 3. So that's, I'll simplify that. little bit more. If you have 4 pi I there instead of 2 pi I, you will still get the same formula. So I'll get e to the minus pi root 3 in the numerator, but the denominator, actually, this might not be that simple. Denominator is going to give me, because you're going to take the square of that, and when you take the square of that, you'll end up with e to the 8 pi I over 3, and 8 pi over 3, that's again going to give me negative 3 times negative half. So I'll write this e to the minus pi I again, plus I root 3 over 2. So this gives me negative e to the minus pi root 3 divided by 3/2 1 minus I root 3. So that's the only change you have in the denominator, not the numerator doesn't change at all. So these are the residues, and we have solved this problem.